Hello, everyone. Welcome to this episode of Eyes on Earth. Our podcast discusses our ever-changing planet with people here at EROS and across the globe who use remote sensing to monitor and study the health of Earth. I am your host, Steve Young. Today's guest is Dean Gesh, a research physical scientist who leads the Coastal Changes and Impacts focus area in the Science and Applications branch here at EROS. He and his colleagues at EROS produce coastal elevation models used by government agencies to project the impacts of flood inundation from sea level rise and storm surges. Their work marries topography, or land elevation, with bathymetry, which is nearshore water depth, into what are called topobathymetric digital elevation models, or TBDEMs. The reality is, as hurricanes continue to unleash storm surges from Texas to the Gulf of Mexico and up the eastern seaboard, and as sea levels continue to rise in the Pacific Ocean and exacerbate tidal flooding on low-lying islands and atolls, decision makers need accurate elevation measurements to be able to model impacts and enact measures to help protect the millions of people living in these areas. Dean and his colleagues provide that accurate elevation information. Welcome, Dean.
Thank you.
How do we know sea levels are rising?
Well, like a lot of physical processes that we observe, it's done by observation, different measurements. Typically, a way that sea level rise is measured is with long-term tide gauges. Most people are probably familiar with the tide as it comes and goes, high tide, low tide. In between there is something we call mean sea level, or the average tide level. Averages out those high tides and low tides. So we track changes in sea level, the mean sea level, with these tide gauges. They're fixed measurement stations that are on the shoreline, and they measure very precisely the water level. And if you do that over a long time period, then you can track how the sea level is changing over time. We also use satellites. Since the early 1990s, there's a type of satellite called a satellite altimeter, which uses radar technology to measure very precisely the height of the ocean. So there's a satellite record, which is then compared to and correlated with the tide measurements. And those are the main two ways that we know that sea level is rising, or sea level is changing, mostly rising in different locations around the Earth.
So to the degree that sea level is rising in different places, what's causing those rising levels? Where are those rising levels coming from?
Well, there's a number of different factors, but we can summarize it probably in just two. Primarily, melting of land ice is the big one. So that would be Antarctica and Greenland, and two very large land masses that are covered by polar ice caps. One thing to note is that sea ice, or ice that's floating on the ocean, like in the Arctic area, when that melts, that doesn't change sea level. It'd be analogous to having an ice cube floating in a glass of water. And when that ice cube melts, it doesn't change the level of the water in there. So that's a distinction we need to make. But ice melt that's on the land surfaces is a big component that changes sea level. And then the other big one is what we call thermal expansion. And that's simple. If you remember back to your maybe elementary school science classes, where liquid expands when it heats up, and that's exactly what's happening. A lot of the increasing heat in the climate system ends up in the ocean, and as the ocean warms, it expands, and that raises water level. So those are the two main components.
So is sea level rise and the rising levels uniform across the planet or not?
And no, they're different. The term that we use, and I've used it already, is mean sea level. Global mean sea level is somewhat difficult to define, and it's really it really doesn't exist. It is different depending on where you are on the global surface of the Earth. That can be averaged across, but there are large regional differences. For instance, in the central Pacific Ocean, a lot of the projections for increasing sea level the rest of this century show that to be higher than the global average sea level. And another place is on the northeast Atlantic coast of the U.S. That's another area where the sea level would be rising faster than it is on the global average. And that's due to a couple different things. Ocean currents is a big one that has an effect. Ocean currents vary around the surface of the Earth. Gravity, variations throughout the globe. That changes, the height of the water, the height of the oceans. And then another one is the land surface itself. In some places, the land surface is actually subsiding or sinking. It's the term we use as subsidence. In other places, the land is actually rising. So we use a term called relative sea level rise. So that's relative to the land surface. So where the land is sinking and the ocean is rising, you get effectively more sea level rise. Where the land is rising, the ocean might be rising as well, but it will be effectively seem like a smaller increase or even a decrease in sea level if the land is rising faster than the water. Yeah, so there are great variations around the globe.
So talk about some of the dangers posed to coastal communities and people living in those communities as sea levels rise, as high tides become even higher, and as storm surges increase. What are some of the dangers posed to those coastal communities?
A simple way, but a good way to think of it is you have a higher platform, if you will. So storm surges, those waves and higher water levels, if that starts on a higher platform, and in this case, the platform would be the base ocean level or the mean sea level. So if that's higher, then anything that's on top of that is also going to be higher. So as those waves propagate inland, they're going to reach further inland than they had historically, and the damaging effects of that, erosion, shoreline erosion, that sort of thing, flooding, anything that's associated with that is going to take effect further inland than it would have because of the base platform being higher. High waves, again, they can reach further inland if they're on that higher platform. And then there's also a term that's got a lot of attention in the scientific community lately, and that's called nuisance flooding. Interesting term that's associated with that is sunny day flooding. So this is when there's not a storm. And that's just the noticeable increase in the high tide level. So there's things called king tides, certain times of the year when the tides are generally higher. But again, if the base platform, if you will, of the ocean is higher, then those high tides are going to be much more noticeable. And that's been called nuisance flooding or sunny day flooding. And that's being observed quite a bit more than has been in the past.
You and your colleagues here at EROS and with CONED, which is the Coastal National Elevation Database, map coastal elevation. How do you do that? What are the tools you use to map coastal elevation?
We use satellite technology, both satellite imagery and other types of satellite data, radar data. We also use airborne, or what we call aerial photography, or an instrument that's carried by an airplane called a LiDAR. That's a laser instrument that measures elevation very precisely. That's a big one that we use. LiDAR can also be used to measure the depth of nearshore waters and specific types of LiDAR. And then we also do traditional ground survey for very detailed points. And then lately, what we would call UAS, unmanned aerial systems, or commonly known as drones. So those are small platforms that, again, would either use a camera to take pictures, photography, and translate that into elevation data. And now drones are starting to carry LiDAR instruments as well. So we use a whole suite of those instruments to measure and map coastal topography.
And when you talk about near shore elevation or land under the water, there are tools that allow you to judge that depth fairly accurately?
Yes. Just like measuring the elevation of the land or the topography right next to the water, there are several tools. The traditional way that that's been done is from boat surveys, what we call hydrographic surveys. So that would be sonar, instrument that sends out sound waves and measure depths. And we still use that type of data extensively. When you get very close to the water line, to the shoreline, very shallow areas, that becomes more difficult for those instruments to use. And that's where these other aerial remote sensing instruments, like you mentioned, bathymetric LiDAR, visible imagery, photography, and satellite imagery to measure those depths as well. The LiDAR is what is called an active instrument, so it sends out a laser pulse and then measures the response from that. The imagery, satellite imagery, and aerial photography, whether that's from an airplane or from a drone, is what's called passive. So that measures the reflectance, the sunlight reflectance. And in certain bands or wavelengths of the spectrum, that can be measured with those photographs and those satellite imagers. And then that can be processed to depth information.
And how accurate is all of it?
It varies. It can be highly accurate. The LiDAR would be the most accurate. And then also the sonar, the boat. A little less accurate would be the imagery from satellites that are used to derive that. It's on the order of a few feet in best cases from the satellite platforms, and then on the order of several inches or a foot vertically from some of those other sources.
I think a key challenge in your line of work is something called vertical uncertainty. What is that, and how do you try to address that in the work you do?
Right, vertical uncertainty. It's one of those terms that can get a little tricky, uncertainty. Sometimes when you say uncertainty, that can be interpreted as saying, well, we're just guessing because there's a lot of uncertainty. In the scientific realm, that's not the case. Uncertainty, there's error associated with any scientific measurement. Now, we do the best job we can to reduce those errors, and the instruments keep getting better and better. But the term vertical uncertainty is maybe just a fancy term for the error that's associated with any scientific measurement. So really the whole idea there is that the data we're using, make sure it's appropriate for the application. There's many different scales of mapping and scientific study from remote sensing data, some very local. So there you would need very high resolution, high spatial resolution, and very high vertical accuracy. If you're trying to cover much more broad areas, you can get by with less resolution and less accuracy. So the idea there is that as we map the coastal topography and the bathymetry, if we're trying to look at very small increments of water level increase, in this case sea level rise or storm surge flooding, that we have very highly accurate elevation data so that we can model those very accurately.
It seems like you folks at EROS have been enlisted to assist in sea level rise work at some fairly exotic locales, places with names like Majuro, Ponape, even Hawaii recently. Give us an idea of the kinds of things you're assisting with when you go to places like that.
Yeah, it's been great working in some of those places. One of the benefits of working in coastal areas and as a geographer, being able to travel and work in those places is just tremendous. But those are places that are on the forefront of climate change impacts, island locations. That gets a lot of attention in the press. Small island nations and vulnerable areas again to sea level rise. So Majuro is an atoll in the Republic of the Marshall Islands in the Central Pacific, and what we were doing there is working with a number of local groups to produce inundation maps. So under specific water level increases that again could be from storm surge or sea level rise itself, or more likely a combination of the two. So the mapping that's been done of topography and bathymetry in a global sense is not detailed enough in that area. They're very low-lying islands. So what we did in Majuro was used a drone-based approach, again, a UAS or unmanned aerial systems, and a lot of ground survey to collect very detailed, very accurate elevation information, and then process that into inundation maps, risk maps of inundation at various levels. So that was a successful project there. Ponape is in the Federated States of Micronesia, also in the Central Pacific, and a little bit different there. It's a high relief island fringed by mangrove forests, which are forests that grow in the tidal areas around the island, but also very susceptible to effects of sea level rise. And mangrove forests are in tune with the tidal range, and as sea level rises, they're adapted to growing in saltwater environments, but are still sensitive to that. There's a wide range of species. So the work we did in Ponape, again, looking at how sea level rise might affect the resiliency of those forests. They're very important ecologically around that island. And again, it's all tied to elevation, very accurately measuring elevation along the shoreline. And that's the expertise we brought to that. And then our latest work in Hawaii that you mentioned, that is a coastal inundation assessment for an area of very valuable cultural resources. That was work that was done collaboratively, is being done collaboratively with the National Park Service. They're very interested in again, how these very valuable cultural resources, archaeological sites, at this particular location on the Big Island of Hawaii are going to be threatened as sea level increases and as storm surges increase and that sort of thing.
You get the sense sometimes that as sea level continues to rise, that some of these low-lying islands and atolls will simply disappear at some point in time. But is the information you're providing, the elevation data you're providing, I mean, does that get used for any kind of efforts to protect these islands or to protect these cultural sites? I mean, what do they do with the data that you provide?
What this shows is if nothing is done, if there's no mitigation that's done, if there's no planning and the sea level rise, it happens like it's projected to, what would be the effect of that? So that helps planners on the ground and in those locations look at vulnerable places and say, okay, if we do nothing, this is the projection of what could happen. Erosion along the shoreline, damage to these either natural or cultural resources, that sort of thing. But then also going along with that is, okay, if this is the kind of damage we would expect or the kind of impact we would expect, what would happen if we built a seawall here, or if we built other protective measures or move some of those resources if they're movable, that sort of thing. So that's what we would call mitigation planning or adaptation planning, saying, okay, this is what's projected to happen in our best knowledge of the projections of sea level rise, and then what can be done to mitigate those damaging effects and plan to preserve these valuable cultural natural resources.
A lot of your TBDEMs are created through the group you're associated with here, the Coastal National Elevation Database Project, or CONED. Are there other organizations or groups that produce similar coastal elevation models, or is the work we do here at EROS unique at all?
I'd say it's unique, but there certainly are other groups that produce these. A lot of these models are done on a very local scale. So you'll see scientific publications or studies where they're done for a specific location. The scale is one thing where we're probably a little bit unique. We do it over very large areas, not national yet, but very large regional areas. Our friends at NOAA do very similar work. The one group at NOAA produces these models for tsunami impacts, what's called tsunami run-up, the run-up of tsunami waves. That's mostly limited to urban areas, which makes sense. That's where people live. So they do that. They're more limited to the area, and they do it at a lesser resolution. We work at a much higher resolution. We're at about a 1 meter spatial resolution, so about 3 feet. But again, it's a collaboration. They use some of our data. We use some of their data. NOAA's very good with hydrographic survey data or this bathymetry data offshore. So we use a lot of their data, and so there's a lot of similarities where our models cross, but they're made for different purposes.
And what does the future hold for the work of you and your colleagues? I mean, will you be going to more exotic locales? Have you got big projects coming up? What can you tell us?
Well, we certainly hope for more exotic locales, but those are hard to predict. Nothing probably in that category, but we do have some big efforts coming up. There's been a significant amount of new LIDAR data collected over coastal Louisiana and pretty far inland. We have an existing CONED model there. It was one of the first ones we actually did, but it's almost a complete redo, and that will be incorporated into this new version of the CONED elevation model. It's really important for what's known as the master plan. There's a group there that we're collaborating with, CPRA, that stands for the Coastal Protection and Restoration Authority. It's a state agency in Louisiana, and they're the ones that are charged with protecting the coast, restoring the coast, planning for the resiliency of the coast. It's a highly dynamic shoreline that's well documented, the damages that hurricanes and sea level rise have brought upon that coastline. So a key component of their state master plan, which is an effort that happens every 5 years, is this very accurate elevation model. And that's what's being produced in this project. We're the main producer of that data. And then that also includes what we call validation of it, the checking, the quality checking and documentation of, again, the uncertainty and the error and the overall quality of it. Another thing that we're looking at in the future is along the East Coast. We've done quite a bit of CONED work along the East Coast, but more the Northeast Coast. So there's an effort that will be starting up later this year into next year. And this is based on the hurricane impact supplemental funding that Congress allocates. So from the Carolinas down to the tip of Florida, basically the Atlantic coast, so the southeast Atlantic coast, CONED models will be developed. These high accuracy coastal elevation data will be developed for that area. And that's important. This is part of the COSMOS, the Coastal Storm Modeling System. This is really the first time that system is going to be developed and deployed on the East Coast. So a big effort there. We're really looking forward to that. And then the last thing that our future holds is a related project, and I'll call it inland bathymetry. We've done quite a bit of work, as we've been talking about today, on the coast. But the water depth information merged with the adjacent land information is just as important for inland areas. And by inland, I mean away from the coast. So that would be along rivers or lakes or reservoirs. There's a concept there that the USGS is developing called the National Terrain Model. We're quite involved with that, doing some initial research and development and testing to figure out how to best map that inland bathymetry and merge it with the topography data for a seamless elevation model across the U.S.
We've been talking to Dean Gesh, a research physical scientist at EROS who is heavily involved in the work of producing coastal elevation models and looking at coastal changes and impacts brought about by sea level rise. Thanks for joining us, Dean.
You're welcome. My pleasure.
We hope you come back for the next episode of Eyes on Earth. This podcast is a product of the U.S. Geological Survey, Department of the Interior. Thanks for joining us.